Gamma-ray burst afterglows are thought to result from the interaction of extremely relativistic outflows with the surrounding matter, with synchrotron and inverse Compton emission successfully explaining the observed spectra. However, the traditional indicators of jet-like outflows, such as achromatic breaks in the afterglow light curve, observed net polarizations, and extremely large energetics, do not necessarily imply jet-like geometries. Many GRBs exhibit breaks that do not fit the jet theory, motivating the consideration of alternative geometries. The authors extend the standard theory of afterglow evolution to ring geometries, motivated by recent numerical simulations showing that ring-like geometries are permissible for relativistic outflows. They present an analytic prescription for the light curves and spectra produced by relativistic toroidal blast waves, comparing these to their spherical and jet-like counterparts. The results show that ring afterglows decay faster than spherical outflows but not as fast as jets. This work is motivated by the need to explain the variability and wide range in observed luminosities of GRBs, as well as the nature of their central engine, which remain topics of deep debate. By considering alternative geometries beyond the traditional spherical and jet-like models, the authors aim to provide a more comprehensive understanding of GRB afterglows. The ellipser mechanism, which produces ring-like geometries, is a promising alternative to traditional jet-like geometries, and the author's analytic prescription provides a valuable tool for exploring these alternative scenarios. Expanding relativistic rings are hypothesized to be a potential explanation for various astrophysical transients, including X-ray flashes, superluminous supernovae, transrelativistic supernovae, and fast blue optical transients. To investigate the dynamics and radiation of these rings, the authors employ a mathematical formalism comprising equations for the kinetic energy of the blast wave, the solid angle of the blast wave, and the characteristic peak frequency of electrons. The authors demonstrate that the light curves and spectra from expanding relativistic rings diverge from those of spherical and jet-like outflows, particularly after a break time when the blast wave begins to decelerate. This divergence could be discernible in the current gamma-ray burst (GRB) catalog, providing a potential diagnostic tool for identifying the geometry of these events. The characteristic peak frequency of electrons is a critical parameter in this context, as it influences the radiation spectrum and light curve. The author's calculations reveal that the peak frequency decreases as the blast wave expands, leading to a softening of the radiation spectrum over time. The implications of these findings are significant for ongoing and future time domain surveys. By analyzing the light curves and spectra of astrophysical transients, researchers may be able to identify the presence of expanding relativistic rings and distinguish them from other geometries. This, in turn, could provide valuable insights into the underlying physics of these events. In the realm of relativistic outflows, two distinct geometries dominate the physics of radiation emission: conical, jet-like outflows along the poles of the source and ring-like outflows in the equatorial plane. These geometries are characterized by their half-opening angles, θ0. To determine the cooling Lorentz factor, the average power per electron per pitch angle is calculated using the Thomson cross-section, 4 velocity, and magnetic energy density. By inverting this equation, the cooling Lorentz factor is derived, leading to the cooling frequency, νc. The spectral flux from a radiating blast wave is also derived, taking into account the redshift, luminosity distance, Doppler beaming factor, and frequency-dependent emissivity. At peak emission, the Doppler beaming factor is given as 2 gamma, resulting in a peak spectral flux that scales with the radius, time, and energy as f nu, max proportional r caret, 32 eta, 1 plus 2 eta. The self-absorption of synchrotron photons is considered, and a simple scaling for the self-absorption frequency is derived, depending on the radius, time, and energy. Finally, the paper computes light curves for a constant density medium, assuming a spherical geometry. This allows for comparison with the spherical and jet-like geometries derived in Sari et al. 1999. The calculations are based on the constraints derived in the previous sections, providing insights into the radiation emitted by relativistic outflows. The spectral flux for ring afterglows at low frequencies is derived, assuming self-absorption of photons. For frequencies below the self-absorption frequency, the flux is proportional to nu-2, whereas between the self-absorption and characteristic frequencies, it is proportional to nu-1/3. This distinction allows for differentiation between spherical and ring-like geometries. The slopes of the flux evolution are distinct for spherical and ring-like geometries, with the latter exhibiting a shallower decay. In contrast, the jet geometry exhibits a steeper decay, with a slope of t-1/3. At high frequencies, the light curves follow distinct power law decays for cooling and non-cooling electrons. The ring afterglows exhibit two distinct cooling breaks, analogous to those calculated for spherical outflows. The power law index of the electron distribution, P, plays a crucial role in determining the decay slopes. The calculations reveal a clear distinction between afterglows produced by relativistic rings and jets, with ring afterglows exhibiting shallower decay slopes throughout their evolution. The graphical depiction in Figure 2 illustrates the distinct features of ring afterglows, including differences in cooling breaks and decay slopes. The implications of these findings are discussed in the next section, where the implications for classical GRBs and the jet model are explored. Observations of shallow breaks in some light curves, such as GRB 030329 and GRB 221009A, are difficult to reconcile with the jet framework, suggesting that ring afterglows may provide an alternative explanation. Equations 1316 summarize the derived flux relations for ring afterglows. F_nu less than nu_a, nu_a squared nu_m caret 1/3, F_max, r squared, 13, F_nu less than nu_m, nu_m caret 1/3, F_max, r caret 2/3, 14, F_nu_m less than nu_c less than nu_c caret 2, r cubed nu_m caret P1, 2, nu_c caret P2, 8, 15, F_nu_m less than nu_c, nu_m caret P1, 2, 8, 16. These equations capture the distinct features of ring afterglows, including the power law decays and cooling breaks, and provide a framework for understanding the temporal evolution of these events. This research paper delves into the dynamics and observational signatures of expanding relativistic rings in the context of gamma-ray bursts, GRBs. It explores a scenario where these rings preserve the notion of beaming, which can account for shallow breaks observed in many GRB light curves. Unlike traditional jet models, this geometry does not require a complex central engine to achieve its configuration. The paper is inspired by the work of DuPont et al. 2022, where rings arise naturally, albeit with lower energy than needed to explain cosmological afterglows for the conditions considered in that work. The authors emphasize that the importance of their calculations lies in the unique features presented by the ring geometry, while the energetics can be adjusted to match the observed phenomena. In terms of specific findings, the paper highlights the case of GRB 221009A, which favors a broken power law model in the X-ray with flux decay slopes steepening from t-1.498 plus or minus 0.004 to t-1.672 plus or minus 0.008, with a jet break time of Tb. X-ray approximately equals 8 times 10 to the power of 4s. The timing of such steepening might be due to a jet with a half-opening angle of 3.5 degrees. D'Avanzo et al., 2022. However, the light curve does not steepen beyond the decay index greater than 1.7 f nu t after the break, and observers cannot match this shallow X-ray decay index with what is predicted using a simple Onexus top hat jet. For typical values p approximately equals 2.4, the top hat jets predict alpha greater than 2, but rings predict 1.63 less than alpha less than 1.77. Well within the required range for GRB 221009A. Therefore, one can interpret this GRB as stemming from either a more structured jet configuration or an expanding relativistic ring. The notion of some astrophysical transients being sourced from expanding relativistic rings, rather than jets, has several implications. A The probability of viewing ring afterglows is larger than that of jets by a factor 2, theta 0. A blast wave with a half-opening angle of 0.1 radians, if oriented as a jet, would cover 0.5% of the sky, while an expanding ring covers 10%, larger by a factor of 20. As a result, ring geometries, as compared to jet geometries, bring down the required source rates significantly. B. As demonstrated by DuPont et al. 2022, relativistic rings can be born purely from geometrical and hydrodynamic effects as opposed to the more complex central engines required for producing classical jets. C. The late-time evolution of the relativistic ring is much more stable than the jet since the spreading of the relativistic ring is effectively unidimensional and is therefore a candidate for light curves with shallower breaks. D. Around the time of the ring break, when the emitting patch is no longer locally spherical, the specific intensity, surface brightness, is no longer symmetric about the line of sight to the observer for a general viewing angle. Greneau et al. 1999b. C. Greneau, 2007. Van Eerten et al. 2010. This fact can act as a useful probe for the underlying dynamics of rings, which can be further detailed by direct hydrodynamic simulations in the near future. Detailed analysis of scintillation patterns may be sensitive to the surface brightness distribution, Goodman, 1997, and may help distinguish jets from rings. This letter has considered synchrotron emission, which is more readily observed in radio and optical frequencies. At higher frequencies, inverse Compton emission may dominate. Adding the inverse Compton component could be done in a similar way to Sari and Eason, 2001, or its extension by Nakar et al. 2009, if Klein-Nishina corrections are important. Please provide the content that needs to be refined. I'll transform it into a direct, concise, and technically accurate summary suitable for voiceover narration, following the guidelines you provided.